Hello again, my dear students, and welcome to the second part of this lecture, or maybe this section dealing with the interfacing circuit associated with the piezo-based sensors. In the first part, we have demonstrated together two different types of piezo-based interfacing circuits. We have demonstrated what we can call the piezoresistive interfacing circuits, where the variation in the sensor is reflected as a variation in resistance. And we demonstrated different architecture in order to implement a resistance to voltage interfacing circuit, either using a very simple potential divider or maybe using a differential amplifier. Then we have also discussed together what we can call a digital or an on-off switch, where we have also shown some interfacing circuit compatible to this type of sensors. Now, in this part of the lecture, we are going to illustrate some circuits compatible with what we can call a piezocapacitive sensors. So, as we previously mentioned, a piezocapacitive sensor is these sensors that convert the variation in the force, pressure, frequency, or whatever piezo effect detected into a variation in capacitance. And we also have discussed together that we need to convert this variation in capacitance into a variation in voltage. So the main role of such interfacing circuit is to convert capacitance into voltage. Let's see different topologies toward this aim. One of these topology is this basic topology, which I think we can easily consider its implementation. The first block, for those who have studied with us electronics 3, I think they will be somehow familiar with the first block. And this is a very standard second order filter with two capacitors. As you can see here, we have RF and CF as a fixed feedback capacitors, and we have then CX here, which represents the sensing capacitance. So whenever your sensing element change, the value of CX will change accordingly. So let's see how this circuit can act as an interfacing circuit for a piezocapacitive sensor. And as you see, my dear students, this circuit is then followed by an amplifier circuit to amplify the voltage. It's a very basic non-inverting amplifier to amplify the voltage to the targeted level. Let's see together how we can use this circuit as a piezocapacitive interfacing circuit. Okay, so as we see together, we have here we have here a input voltage applied to a capacitance, which is CX. And then we have our input operational amplifier. This is the negative, and this is the positive. And this is connected to ground. And then we have this feedback capacitance and feedback resistance. So this is the first stage. This is CF, and this is RF. And this is the output of the first stage. So let's discuss this circuit together. As you can see, my dear students, we have here these two parallel branch. Of course, we are dealing with an ideal operational amplifier. So let's call this Vin or whatever. And this is, as you see, this is an ideal operational amplifier. So this is a virtual ground. which simply means that the current flowing in this capacitor, Cx, will be simply branched to move in CF and or RF, or the parallel combination of these two capacitors. So if you remember from your electronics 3 classes, when we have this parallel combination, we can see that the admittance, which is 1 over the capacitance, 1 over the impedance of this parallel combination, is simply SC plus SCF, sorry, 1 over RF, or simply Z feedback equals to 1 over SCF plus 1 over RF, or you can rewrite this in a form of ZF equal R over 1 plus SCF RF. So this is the equivalent impedance for this feedback network. So the current flowing here in this Cx will typically flow in ZF. So as you can see here, we can write an equation. Again, don't forget this. So this current, which is V input minus 0, which is the V input, over 1 over SCX, will equals to this current, the current flowing here, which is equal 0 minus V output, so it's V out over the equivalent feedback impedance, which is R over 1 plus CF times RF. So we will write this here, RF over 1 plus SC times SCF times RF. So this is simply that equivalent value of the current, and this is a nodal analysis for the circuit. So simply here we can write it like that: V input times SCF equals minus V output over RF times 1 plus SCF RF. Of course, this is Cx, not C. This is C plus. Or we can write it also in a very easy manner. So V output over V inputs equals 2. So we will get this right that. So it will be RF SCX over 1 plus, and there's a negative sign here, don't forget it, over 1 plus SCF RF. So this equation, as you see, my dear students, represent typically the transfer function of your circuit, where this transfer function is directly proportional to the value Cx, which, if you remember, represents the sensing element, which is in our case a piezocapacitive material. So whenever the Cx change for a fixed V input, you will have a change in the V output correspondingly to this Cx. Regarding this negative sign, you will easily get rid of this negative sign, as if you remember, we still have an inverting amplifier cascaded to this stage. So simply the next amplifier will have a gain of, if you remember, minus R2 over R1. So this minus will cancel this minus, and you can use this R2 over R1 in order. So we can use this R2 over R1 in order to tune your sensitivity or your transfer function. So here you have a direct relation between the output and the capacitance, and you have controlling elements here. This R2 over R1 is an amplitude controlling element. You can control the amplitude of your, or the slope, let me say, of your transfer function using R2 over R1. And still, don't forget that RF over 1 plus S, 1 over 1 plus STF RF is a capacitance behavior. This is one model for a filtering behavior. So when you have a DC response, I mean, when omega is equal to 0, don't forget that this S is typically a J omega. So when omega is equal to 0, this simply will makes this S equals to 0, and then you will have an RF or a DC gain equals RF, because the denominator will be equals to 1, keeping RF in the denominator. Whenever this S tends to infinity, that simply means that the overall term tends to 0. So this is some sort of a low-pass filter embedded in your interfacing circuit that can get rid of any high-frequency component imposed to your signal. So I think this is a very typical circuit that can be used for converting a capacitance into some sort of a voltage variation, and you can tune your voltage variation based on R2, R1, RF, CF. These are all an adjusting parameter, keeping V input constant. So whenever CX change, V output will change accordingly. So this is a very typical and good example for having an capacitance to voltage interfacing circuits. Let's go to another type of, or another model for capacitance interfacing circuit. So this is the first model. So this is also another similar model for a capacitance interfacing circuit. Herein, we use the same concept for a potential divider. If you remember, when we had a resistance, if you remember the schematic, when we have a resistance sensor, we typically use a potential divider in order to convert the variation in the resistance into a variation in voltage, if you remember in part number 1. So in a similar manner, we can use this capacitance as a potential divider. Simply, you can use this equivalent capacitance as a potential divider. So for example, let's say that this is C1 and this is C2. So we can use this C1 and C2 in order to make a capacitance divider. So let's see how we can make something like that in our case. Perfect. Okay, so this is very simple. Let's say that we have something like that. So here, if this is C1 and this is C2, then we can say simply that this is have an equivalent of 1 over SC1, and this is have an equivalent of 1 over SC2. Then the voltage here, V out, is equals to 1 over SC2 over 1 over SC1 plus 1 over SC2 times the V in a very simple manner, which will lead to, simply if you multiply by SC1, C2, you will have C1 over C1 plus C2 times V in again, of course. So this is simply how it works. So if C1 or C2 is a variable capacitor or a piezocapacitive sensor, whenever the capacitance changes, so for example, if we consider C2 as a piezocapacitive material, whenever C2 changes, the output will change accordingly to this equivalent value for C2 and so on. So this is a model where you can use this potential capacitance in order to vary. But here we have to consider some very important points. The first point is, as you already typically know, capacitance can only have this capacitive effect or impedance effect far from a DC, because simply if you substitute here with omega equals to 0. Again, don't forget that this S is J omega. So if you substitute here by S equals 0 or J equal omega equals 0, which leads to an open circuit. We all know that capacitance are treated as an open circuit in DC analysis. So we cannot do this implementation, this potential divider, we cannot do it in a DC format, because simply in a DC, these two capacitors will be some sort of an open circuit. That means that your V input, the voltage applied between these two terminals, should be typically some sort of an AC signal. That's why if you return here to the slides, you will find that here we use some sort of a square wave signal or some sort of a pulse signal to feed these two branches like that, so that they can have a capacitance effect. And here the effect of the impedance, or sorry, the effect of the frequency is diluted because simply you are using a ratio between C1 and C2. That's why the S impact is not in, but still it should not be equal to 0 to avoid an open circuit behavior for that. So this is a first important comment. A second also important comment is when you make this pulsive signal, that simply means you are enforcing your capacitors in what we can call a charging discharging cycle. So when the voltage is high, your capacitors will act to charge. When the voltage is low, your capacitors will act to discharge. And herein, you should have a discharging element. Otherwise, you will not have this variation. Your voltage will be saturated, because simply if you don't have a discharging cycle, your voltage will be kept high all the time, because simply the capacitor couldn't find an element to discharge in. And that's why we add this resistance. So the job description of this resistance is simply to be used as a discharging element. When the voltage tends to low, the capacitors will discharge in this resistance, and then this voltage will drop again to low and so on. So you can tune the discharging time by simply tuning the RC value. All of you know that this RC value is the factor determining the discharging time for any discharging capacitor. So this is a very important information here. So, as I just mentioned, the role of this resistance is to guarantee a discharging path for those capacitors. And you can easily control the level of discharging, or what we can call the level of fluctuation in your voltage here. You can easily control it through controlling the value of R and C together to control the discharging length. Then, as usual, such potential dividers are not isolated in terms of a loading effect. That's why we usually use this cascaded buffer in order to isolate the signal with respect to what is next in terms of the system. And finally, we use this non-inverting amplifier as very standard non-inverting amplifier with a gain 1 plus R feedback over R series, or R2 over R1, whatever, to control the voltage gain applied to this circuit. So you can see this circuit as 3 cascaded units. First, we have these potential dividers using the 2 seriously connected capacitors. And don't forget that we impose this pulsive signal in order to ensure an alternating voltage compatible with the nature of the capacitors. And then we have a buffer, and finally we have the non-inverting gaining unit in order to ensure the reasonable gain of our system. As I just mentioned, maybe in the previous part, you cannot stop with having different topologies for cascaded systems. So here you can find a collection of capacitive interfacing circuits with different cascading topology. For example, here we have two terminal voltage connected between two capacitors, and these two capacitors representing two sensing elements. And then we have a buffer. This is a typical buffer connected. Or you can add this frequency model or a filtering model here, as you can see, with still a buffering phenomenon. Or you can add another terminal buffer here as a third element, or you can add an amplifier. As you can see here, we have an amplifier. This is an amplifier signal, and we have here a filtering response with here a multi-stage cascaded unit. So all these are different examples for different structures that can be used for implementing a capacitive-based interfacing circuit. I invite you to start using this capacitive interfacing circuit in order to start examining different topologies. Maybe this will be part of your practical tutorial in order to solve more problem with that. And I would recommend applying this case study. This is a very recently published paper, considers the utilization of a piezocapacitive material in order to fabricate a blood pressure sensor. As you can see from this graph, they start to apply certain forces on the material. The forces here is measured in Pascal, starting from 1 Pascal in figure A up to maybe 100, I think 100K Pascal here in figure D. So this range illustrate different points for the piezocapacitive applied pressure, and corresponding to each point, you will find a ratio between C to C node, where C node represents the variation in the so C node is representing the initial value of the capacitance, or the initial value of the piezocapacitive material, and C represents a variation in that. So, for example, if we consider the 1 Pascal model, we will find that there is a ratio of 0.06%. I mean that the capacitance, it changed 6% with respect to C node. So it's 1.06 of C node. When it become to 2 Pascal, this may be 0.08. When it become to 5 Pascal, this reach about 0.14. It's for 14% increase in the capacitance, and so on, until we reach the 100 kilopascal, which is 16 times the capacitance. So delta C over C node is 16 times the capacitance. So you can first, what I can recommend for solving this is first to plot what we can call the transfer characteristics. Simply, the transfer characteristics here will be in a form of, so let me use a pen. So the transfer characteristics here will be something like that. Just let me make it in a correct. So here the Pascal, the voltage applied, sorry, the pressure applied in Pascal, and here this will be delta C over C node. And you will have some sort of an increasing function. It will not be a linear function, by the way. You will find something like that maybe. Starting from the minimum pressure, which is 1 Pascal, up to the maximum, which is 100K Pascal. This represents what we can call, my dear students, the limit of sensing. So the limit of sensing here is from 1 Pascal to 100K Pascal. Then you can determine what we can call the sensitivity. The sensitivity is simply the minimum variation in input that cause a variation in output. So if we move from 1 Pascal to 2 Pascal in this range, you will find that your output capacitance will change from 0.06 to 0.08, which means that in this range, the sensitivity is 0.02 delta C over C naught. However, take care, as far as this is not a linear sensing process, that means that your sensitivity will act to change based on the range you are changing. So the range you are measuring. So simply, if you go to measure the sensitivity in a relatively high range at, for example, 100K Pascal, you will find a different value. So first you plot that transfer function, then you start to determine the limit of sensing and the variation in the capacitance and so on, which is the sensitivity, and then you start to propose an interfacing circuit. You can go to the lecture where we demonstrated different interfacing circuits. You can propose from your side different capacitive interfacing circuit, and then you can start evaluating this interfacing circuit. What is good, what is bad, the pros and cons. Maybe some of these circuits will be so simple, but they have a problem regarding loading. Other may be a bit complicated, but we will pay more power and more energy in order to operate and so on. So this investigation, you can demonstrate it, or you can discuss in a very detailed manner when you start doing this interfacing circuit with different topologies. So I will leave this for you in the tutorial, so you can do this step by step. As I just mentioned, I will propose that you can use different circuits. As you can see here we have different topologies. You can use different circuits. I would recommend that you can use, for example, multi-sam, cadence, or whatever, in order to simulate these circuits as well and to see the impact, or as I just mentioned, the pros and cons of each circuit with respect to other circuits in order to make an interfacing circuit for a piezocapacitive material. So that's all from for this topic. We will terminate this at an end for the interfacing circuit, and maybe in the next lecture we are going to start a new topic in our selected topics in electronics module for this year. Thank you very much for your concentration, and see you in the next topic, inshallah. Thank you.